Hello and welcome, Global Climate Change students. This is lecture 5. I have a little bit for you guys to read down here, but before I actually go through the lecture, I just kind of wanted to go over a few things. First of all, we have a test next week. This is going to be the study guide. I will be putting this up on Canvas today, basically. So this would be your first study guide. I'm going to open up the first midterm on Monday, basically this next upcoming Monday on the 30th. It'll be good for the week, but you can only take this test one time, and I'm thinking I'm going to time it, something where you're not going to be rushing to get through it, but at the same time, you're not going to have 6 hours to complete it. It will be administered online and labeled as a quiz, and you can find it under the assignments tab or on the home page in next week's module, right on the home page of Canvas. So that means that there'll not be an assignment this week. I'm going to put up a discussion, but it's basically going to be like question and answer for you guys to be able to use as a resource while you're studying for this exam. So we will have a short lesson this week, and we'll also have a short lesson next week. So basically the test or the exam will be over these 5 lectures, over the first 4 activities here that we've already done, the readings that we went over, basically what we've done in the class so far. The format of the test will be multiple choice questions, some short answer questions, some fill in the blank questions, and probably some extra credit questions. I'm not sure exactly how many yet. I did put some questions in here for you guys to complete. This is quite a bit of information. I'm probably not going to test you by any means on all of these things, but I wanted to make sure that I had everything on there that I might potentially test you on. Okay, so let's get to the lecture. So this week's lecture is going to be over natural forcing factors. There's a number of things that will naturally actually change our climate, and that's what we're going to be going over today. So first of all, you can see, by this graph here, we have, I think we went over this once before, but we have CO2 concentration of parts per million here on the top and temperature here on the bottom with time on the x-axis here. You can definitely see that there's a huge correlation between the CO2 and the temperature of the planet. Now, if you notice, this is 400,000 years ago up till, basically present time. Present time meaning 1950, but really when you're going 400,000 years, that's present. So this has a lot of data in it. It goes back quite a long way. So we can be confident, when we do put these things back to back, and knowing the fact that the CO2 and the temperature are very much correlated. Now, we did just hit a milestone as far as CO2 goes. We did hit 400 parts per million. Basically, this I took actually in May. So during the month of May, we hit 400 parts per million. A couple months ago, for a few days, we did actually hit 415 parts per million. So, we are just getting more and more CO2 in our atmosphere, which is going to change our temperature. Because there is a certain lifetime, CO2 will actually stay in the atmosphere for 10 years or so. And the last time we were hit, like we had this much CO2 in our atmosphere, there wasn't any human life on the planet. So, basically going to natural climate change, there's 2 different things here. There's going to be external forcing factors and internal forcing factors. Now, external ones are going to be where the agent of change is outside of our atmosphere system, off the planet basically, and internal forcing factors is where the change will be inside the Earth atmosphere system, so within our atmosphere. Now, a couple of the external forcing factors will be variations in solar output, orbital variations, and meteors. Well, internal forcing factors would be things like volcanoes, plate tectonics, and changes in atmospheric composition. So solar variations, what I mean by that basically is more sunspots correlate with more solar energy. Okay, we have more solar energy, more sunspots, more radiation coming from the sun. It's going to increase the output of the sun. This is going to be, basically what it looks like, zoomed in on this B picture where, further away you can see the sunspots in A. Now, sunspots are caused by an intense fluctuation in magnetic field of the sun, where their temperature is going to be about 3,500 to 4,500 Kelvin, but the surrounding regions will be 5,500 Kelvin. So, that's why they're darker in appearance, because they're not as high of a temperature, um, or lower intensity of radiation emitted. This is going to kind of show you, what our sunspots are going to look like. This is what our mean looks like. This is going to be in the 1990s, where this is going to be in 50, 60, 70, 80, 90. And you can see here that there's definitely going to be a cycle to our sunspots. You can see here, right there is this picture here, and this blue spot here is going to be this picture here. So you can kind of see how this is, more sunspot activity than, this one or this one or this one, or really any of them here. Whereas these, it starts with high activity over here and then ends right here with almost no activity right here. So you can see how that definitely would increase the amount of output that the sun actually would produce, and it also has a variation or a cycle to it. This is going to be our solar cycle sunspot number progression. This is through January of 2018. Right there. These are going to be predicted values, where these are going to be our smooth monthly values. So you can kind of see as of January of 2000 how, we kind of were at a peak up here, and then we came down here with a pretty good minimum in 09. In 13, 14, 15, we were another high again. We're, right now we're at a low. And even though we're at a low right here in sunspot activity, and that would increase the solar output that the sun would produce, we're still seeing, extremely high temperature, really record high summers. So, we know that even though it is something to take into account, it's not the reason why we're seeing the warming that we have. Okay, so the sunspots increase and decrease over an 11-year cycle. These have been observed for centuries, so we know them, we can understand them and build them into our models. And individual spots last from a few hours to months. And studies do show that the sun is, in fact, about 0.1% brighter when solar activity is high. 0.1 doesn't sound like a lot, but the sun has a lot of output, so it actually is quite a bit. And then here basically is our 11-year average, with our 1-year averages right here. So you can kind of see how we're seeing that kind of cycle going on. Now, the Maunder minimum was a time between 1645 and 1715 where there was an absence of sunspots. This was well observed. Okay, this also coincided with a cool climatic period in Europe and North America. So this is what we would consider the Little Ice Age. So a lot of people would actually contribute that to less solar activity. Okay, so to kind of go also into our Earth and the Earth cycle, or the way it revolves and its tilt and all of that, what would happen if the Earth's tilt was to decrease? How would the summer temperature change at our latitude? Now, in order to think about this, you're going to kind of want to think about the fact that when are we closest to the sun? When is our planet closest to the sun? So our planet is actually closest to the sun during the northern hemisphere's winter. Okay, but the reason why it's actually cooler during the winter is we're actually tilted away from the sun. And we're going to go around the sun, and then we're going to actually be tilted towards the sun during the summer. So if the Earth's tilt was to decrease, how would the summer temperature change? We would actually have cooler summers, because then our tilt would be further away from the sun. Now you can see that Earth's orbit is going to be an ellipse. Okay, here's basically, going to be the center of the ellipses right here. I'm trying to point with my hand on the screen, as if you guys can see it. Anyway, so, we're going to actually have like the sun right here. You can see that, during perihelion, um, we're going to be closest to the sun, and then in aphelion, we're actually going to be furthest away from the sun. You can also see right here, we do go through these solar cycles due, to the Milankovitch theory. Guess not. Okay, so an eccentricity is basically going to be where we're going to have that difference in the solar, um, our path around the sun, and we're going to go from being more circular to more elliptical. So what that means is, you can see when we're more circular, we're actually going to be, closer during perihelion and aphelion, um, and further away actually during the equinoxes, which by the way, today is an equinox. Okay, and then we're also going to have precession, and this is going to be, so precession is going to be where the Earth's axis is actually going to completely change its orientation. So it's going to basically go from like being like this at 23.5 degrees to being like this. So what that means is our seasons are actually going to flip because of the fact that, during the winter where we're actually tilted away from the sun, if we flip that axis, then we're actually going to begin to be, closer to the sun. Just kind of show you that too. Okay, so now this actually is going to be kind of like a wobble of the Earth's atmosphere, and this is going to be obliquity. A lot of people kind of talk about it as being kind of like what is this thing here? Like a top when it's spinning, it kind of like is going to wobble a little bit. So it's going to kind of have that wobbling basically. And then here's going to be our frequency of when those 3 cycles actually going to happen. So, that wobbling or the obliquity is going to happen about every 41,000 years, or the eccentricity is going to happen every 100,000 years, and the precession is going to happen 23 to 19,000 years. So, the most frequent one is going to be the precession, and then obliquity, with eccentricity being the last one. Okay, so the next thing we kind of go over is going to be glaciers, which is going to be, we're going to go over the formation of glaciers here. So glaciers are composed of fallen snow that is compressed into large, thick, and massive ice over many, many years. There's going to be growth when the yearly snowfall is greater than snow melt, and there's going to be glacier decay when the yearly snowfall is less than the snow melt. This is going to be kind of what a glacier looks like right here. This is where we get some of that proxy data. And you can see that the sunshine is directly correlated. When there's more sunshine, then there's going to be less ice volume. They go through periods where they don't get any sunshine up at the poles. So they're going to have that lower ice volume during that time period. When Northern Hemisphere installation is relatively high during the winter and relatively low during the summer, glaciers advance. Why would that be? And what about for a colder winter and a warmer summer? So what would happen during those time periods? That has everything to do with the eccentricity, that Earth's orbit and how it changes from elliptical to more circular. So when the Earth's orbit around the sun is more elliptical, the effects of perihelion and aphelion, which is when we're closest and furthest away from the sun, on seasonality are greater. And that's kind of where I was showing you that picture where you could see, the circular versus the oval, and how you can see how during perihelion and aphelion, that would definitely affect our seasons due to the tilt of the Earth. Okay, so, we also have these internal forcing factors. We have volcanoes, plate tectonics, and changes in atmospheric composition. So volcanoes are going to change the atmosphere because, it's not going to always let a lot of sunlight in. So it's going to scatter that light off of the top of these particles here, um, in the cloud that it spits out here. So it's going to actually act to cool our planet because the radiation just can't get through. Now, as far as plate tectonics go, it's going to change the way that our climate is because of the fact that water is going to heat and cool a lot slower than land. So here in the middle, when you have these really large land masses because they're together, you're number one going to have very little rain because it's going to be, the rain is going to be rained out basically. The moisture will be rained out before it reaches the middle here due to topography and a couple other things. But it's also going to have enough of time to heat and cool, like the land is. And the land heats and cools a lot faster and it's more affected by the seasons. Obviously there's a larger ocean area as well. So there's going to be an area that's going to be more temperate. It's going to kind of stay somewhat the same, and then we're going to have this area in the middle here where these continents are. So what that means is there's going to be large amounts of unequal heating and cooling going on, depending on where you actually are on the globe. And then the last thing we were talking about is the changes in atmospheric composition. We can see that this is the Keeling curve, and this is atmospheric carbon dioxide, and this is measured in Hawaii here, Mauna Loa. So you can see how there's going to be an annual cycle in the spring. There's going to be, or in the winter, we're basically going to have higher CO2. And then it's going to go down in the summer. And this is due to photosynthesis and decay and things like that. So that's what these little wiggles here. But, overall, we've been just really increasing our amount of CO2 in the atmosphere steadily, basically, since, this curve starts at 1960 and goes to 2010. So the changes in that atmospheric composition is going to cause our planet to warm more. So that is everything that I have for this this lecture for you this week. Please study for that exam, and I'll be putting it up next week. We'll have another short exam. We talk about feedbacks actually next week, and then we'll go from there. So I hope you guys have a good week, and thanks.